taking the simplest possibilities. We can you remember this matrix column vector 1 0 0 1? We have studied this column vector in Klebs-Kordan coefficients while studying spin terms. Klebs-Kordan, one for spin up, another one for spin down. So this is for spin up and this is for spin down. For fermions, for spin half numbers, the basic vectors on which Pauli's matrices operate. Okay, so V equals 1 0. This is for spin up, and V equals 0 comma 1 for spin down. We are going to get for E plus, we are going to have two solutions, one for spin up and one for spin down. Okay, and we are going to first we will get the solution for sigma dot P. Sigma dot P, already we know that sigma x Px plus sigma y Py plus sigma z Pz, we know already. And of course, sigma x is given by Pauli's operators, which we know already. For this is for sigma x, this will be your sigma y, and this must be your sigma z. So as I said, you are going to add all the components. So your sigma x, I have taken from sigma x multiplied by Px plus sigma y multiplied by Py plus sigma z multiplied by Pz. Very simple one. So your sigma dot P is nothing but, now you multiply with Px, matrix multiplication. So this will, you will get exactly like this. This will become exactly like this. Okay, 0, Px, 0. And here also just include Py, here also just include Pz. So you add all the three. This alone will have diagonal elements. Okay, so this will not have diagonal elements, we know already. Okay, so this is for sigma z, 1 and spin up and spin down, 1 minus 1. Okay, so sigma dot P will be, you add all the three, we will get equation 8.83. Very simple matrix addition. Okay, now we have calculated for sigma dot P. The remaining thing as it is, you just write it. So your W will be E plus mc square W equals C times sigma dot P V. So we can write that equation as exactly for W, which is equal to C times sigma dot P V divided by, we are going to have E plus. So instead of E, I have written as E plus. So E plus mc square. You pull these terms out. Sigma dot P can be written as in terms of matrices. So I have written exactly like this. And your V will be 1 0 for spin up solution. So this is for spin up solution. Now you multiply, matrix multiplication will give you Pz, this becomes 0, so Pz, you multiply this, so this multiplied by this will give you Px plus Ipy, this becomes 0. So we have written exactly in a column vector, it has become a column vector. Okay, I can keep Px plus Ipy as P plus. So this equation, this matrix becomes Pz, P plus. You multiply with this number into a matrix column, you will have W. So one of the components have been found out. Okay, one of the components has been found out. W equals Cp divided by E plus mc square divided by, by Cp plus divided by E plus mc square. Okay, very simple one. So we have found out one component W, one wave function we have found out. Is it okay? Simple one. Similarly, you can go for spin down. So V equal to 0, 1. See, 1 0 we have found out, spin up. So now 0 1 stands for spin down. So same thing, you have to write the same thing multiplied with 0 1. Earlier we multiplied with 1 0. Now you are going to multiply with 0 1. So multiplying matrix operation will give you, this will be 0. This will become Px minus Ipy. This will become 0. This will become minus Pz. You keep this as P minus. Okay, last time we kept it as P plus. So you just keep P minus. So P minus Pz in a column vector. You multiply this will give you this matrix in a column vector. So we have found out another one, W, another wave function. So this is for spin down. We have done for spin up. So spin up and spin down for E plus. As I said, E plus will have two solutions. One is for spin up, another one is for spin down. Now you will have to put together, you will have to write in terms of 4 components in a column vector, because U contains U1, U2, U3, U4. We have found out U3, U4. W stands for U3, U4. B stands for U1, U2. Correct? So this is what earlier we guessed. Can you remember? Your U will be, capital U will be U1, U2, U3, U4. U3, U4 will have two values, that is for W. Okay, then U1, U2 for B. B is nothing but 1, 0, spin up. And W just now we calculated for E plus this factor. So we have 4 components. This is for spin up and this is for spin down. Okay, this is for spin down. So this is for spin up and this is for spin down. In the same way, E minus has 2 solutions. The same way, E minus has 2 solutions. One is for spin up, another one is for spin down. So this is for spin up, this is for spin down. The corresponding solutions will be like this. So this has now, see, we have calculated for wave functions U1, U2, U3, U4. So 4 components have been found out. Is it okay? Now, suppose if, as we have done earlier just now, if particle is at rest, for non-relativistic case, P tends to 0, P equals 0. At the time P is very less than that of MC. Similarly, if P is less than that of MC, we can say that Px is very less than that of MC, Py also and Pz also. So therefore, at that condition, this will become non-relativistic energy E plus almost equal to m naught c square. We have read somewhere. Okay, m naught c square, rest mass energy. And E minus will be also minus m naught c square, rest mass energy. At the time we will have 1 instead of this, because this becomes 0. This becomes 0. P tends to 0. For non-relativistic case, P will be equal to 0. Okay, non-relativistic case. So this becomes 0. This becomes 0. So here 1, 0, 0, 0. See here 1, 0, 0, 0. This is for U1. Similarly, when you take for U2, this is 0. This is 0. So you have 0, 1, 0, 0. So this is for spin up and this is for spin down. Okay, for E plus. Similarly, you can go for P z tends to 0. So this becomes 0, 0, 1, 0. So 0, 0, 1, 0. Spin up. This is for spin down for E minus. So this is for E plus and this is for E minus. So we have 4 solutions, 4 components exist. Is it okay? As we decrease P tends to 0, the third and fourth components of U1, U2, third and fourth components of U1, they also will decrease. And finally will become 0. Okay, finally this will become 0. Because Pz tends to 0. So Pz tends to 0 means Pz equal to 0. So this will become 0. So 1, 0, 0, 0. So finally it becomes 0. Whereas the first and second components remain the same. 1, 0 exists. So that's why we call this as large components, these two as small components. Okay, so this will be your large component, this will be your small components. Whereas this will be just opposite. This will have large components, this will have small components, this will have large components, this will have small components, because when P is tends to 0 here. Is it okay? So this is what it is given in the slide. So U3, U4, the first and second components are small components. Okay? Is it okay? And to check the completeness condition, so very important 2 conditions to satisfy for any wave function in quantum mechanics will be, one is normalization. Of course, you must have normalization constant should be equal to 1. The probability will never be greater than 1. So we know already this condition. Okay, it should be less than 1. It will be around 1. If it is 1, exact quantum mechanical particle exists, we can say. And another very important condition is completeness. These 2 conditions should satisfy for any quantum mechanical behavior of any particle. It's a very important one. So we are going to discuss, we are going to have the completeness solution. Klein-Gordon equation exists only for 1 component. Okay, whereas Dirac equation says that 4 components. So there are 4 components. U1, U2, U3, U4. 4 components. U1, U2, U3, U4. We are going to check whether normalization constant, normalization condition, and another one is completeness condition, whether they obey or not. We are going to check. So this is U1, this is U2, this is the column vector for U3, and this is the column vector for U4. So these are all wave functions. Okay, 4 components. I am going to take this as a ket vector as two components like plus and plus. The first one represents for energy, sign of energy, E plus. Plus means E plus. plus means E plus. So first component in a ket vector represents sign of energy E plus, and second one spin direction, spin up and spin down. So these two ket vectors represent for E plus. These two ket vectors for E minus. See, look at this minus, first component as minus. So this for E minus, this for E minus, this is for spin up and this is for spin down. Is it okay? I repeat, you have ket vectors. So this can be represented as a ket vector. This is for plus and plus. The first plus represents the sign of energy E plus. Second one represents the spin up direction, spin up and spin down, spin up and spin down. Similarly, spin up and spin down. So we have four solutions. Okay. Now, as I said just now, that it has to satisfy normalization condition and completeness. So normalization goes like this. You have a bra vector, ket vector, that will be equal to 1. See here, just take the complex conjugate, that will give you plus plus bra vector with ket vector, the answer is 1. Plus plus answer is 1. If it is opposite, answer will be 0. If it is spin up and spin down, the answer is 0. Okay, suppose if it is minus minus, we'll see minus minus, see minus minus. What is the answer? Minus minus bra vector with ket vector also minus minus. What is the answer? 1. It will be 1. Good. It will be 1. If it is on the other way around, that also will be equal to 0. Okay, minus plus minus minus will be 0, plus plus also will be 0. Okay, so normalization condition is okay now. Now we will go for completeness. As I said, completeness will be ket bra. Normalization will be bracket. So completeness will be ket bra. This will have a number. This will be an operator. The resultant will be an operator. Okay, so you have a ket vector with bra vector, plus 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 plus. Okay, we are going to add these two. Add these two. Every vector we are going to add. So you have plus 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 plus, one answer. What is the answer? Both will be spin up. Answer will be 1. What is the answer? Come on. Come on. 1. It is not 0. See here. This is E plus spin down. E plus spin down. Answer is? If it is spin up, spin down, answer is 0. Spin down plus spin up is answer is 0. Both will have spin down, both will have spin up. Answer is 1. This is E plus spin down. Answer is 1. This is E minus spin up. Answer is 1. This is E minus spin down. Answer is 1. See, you will have answer as 1. It's an operator, identity operator. Okay, this can be easily checked. We are going to check. And of course, we know that this ket vector can be written as 1 0 0 1. We know already. What is bra vector? Just take the complex conjugate rows and column into the rows. We know already. So this will be your 1 0 0 0. We are going to have tensor product with these two. Similarly, use for this one. This will be 1 0 0 0 1 0 0 0. Okay. Similarly, you can go with. So there's a mistake here. This must be. Any guess? This must be next one. No, it's correct only. See, this is 1 0 0. There's a mistake here. Okay. Anybody can find out. We'll see. Okay. First, we'll have a matrix multiplication. After that, we'll look into. Now you are going to have a matrix multiplication. 1 0 0 0 1 0 0 0. You are going to have a matrix multiplication. So this will become 1 multiplied by 1, this one, 1 multiplied by 0, the next component, 1 multiplied by 0, the another one, 1 multiplied by 0, this another one. Look at this. Okay, so we have now 4 by 4 matrix, 1 0 0. Next one is, this is plus minus. So what will be E plus minus, E plus with spin down. So you have to write 0 1 0 0. So this must be 0 1 0 0. This must be 0 1 0 0. So that's a mistake here. Okay. Similarly, you can go for 0 0 1 0. So this must be minus plus. Minus plus means E minus with a spin up. E minus with the spin up. So 0, 0, 1, 0. So this must be 0, 0, 1, 0. So 0, 0, 1, 0. You will have this answer. 1, 2, 3. You have this answer. The last one is E minus with a spin down. So E minus with spin down. So this must be 0, 0, 0, 1. So you will have 0, 0, 0, 1. So this must be 0, 0, 0, 1. The answer will be exactly 1, 2, 3, 4. The fourth one. Okay. The answer for this one is this one. The answer for this one is this one. Answer for this one is this one. Answer for this one is this one, which is equal to. So there's a mistake here again. So this must be equal to. You add all the four. We have four matrices, correct? Four operations, tensor product. You add all the four. So that will give you, see, diagonal matrix as 1, 1, 1. As I said, the answer will be an operator, identity operator. See, this is an identity operator. For completeness condition, we are going to have get with bra, surely you will have an identity operator. Identity operator. So this is equivalent to identity operator, which is equal to 1. So we can say that sigma E comma S, get E comma S, bra E comma S will give you identity operator, which is equal to 1. So completeness condition also is satisfied. It has to satisfy mainly two conditions, as I said. One is normalization condition, then another one is completeness condition. So thus it is clear that negative energy state solution must exist. So surely negative energy state should exist for Dirac equation. Otherwise the completeness condition will not be satisfied. So it's a very, very important conclusion. Negative energy states exist in Dirac's equation. Now in the next class we are going to look into broadly about the negative energy states. Okay, antimatter, antiparticles, how Dirac has interpreted cleverly. For about 2 years he thought of explaining the negative energy states, and he could explain very clearly. Okay, so this is the solution of Dirac's equation. It's a planar solution, and this equation says that negative energy states exist, and we have seen that, and this solution, the complete solution, exactly satisfies with the negative energy solution. Okay, so we'll stop today. We'll see in the next class. Bye, students.